And it is my great pleasure to introduce Jade Alglave, a professor at University College London and a researcher at ARM. Jade, if you can hear me, hopefully you can, please take it away.
I can hear you. Can you hear me?
Yes.
Okay, good. Hi, everybody, and sorry I can't be here in person. So all the, let me see if I can, I can move my slides. All the work I'm presenting today is done by my team. You can see them here. Most of them work at ARM in an engineer capacity. Adrien, who's in the audience today here, is a PhD student at UCL who's embedded in the team at ARM. And Luc Maranger is working with us remotely from INRIA. So since quite a while now, ARM's memory model has been the subject of a formalization effort, and we write the model in a domain-specific language that's called CAT. And that language drives a collection of tools, in particular a simulator that's called HER7, which takes as input a memory model written in CAT and a litmus test, which is a small example behavior that you can check whether it's allowed or forbidden by the CAT model. We actually upstream extension to the ARM model and the companion tools regularly, and our landing page is here. And we also have a web interface that's hosted on the ARM website over here. And we've written a number of tutorials on how to use the tools and the various extensions we've been working on, and I give pointers to that later. So at a glance, this is what we provide. We have a tool that's called HER-Dimension, that's a simulator, a testing tool that's called Litmus that takes the same litmus tests as input and runs them on hardware and can tell you whether it's seen the interesting behaviors you're interested in or not. We've got a test generator that's called DIY that allows us to generate many different litmus tests in a systematic manner. And this is what the team enhances and maintains and evolves. So the way we do that is by reading the ARM documentation that's called the ARM for ARM Architecture Reference Manual, and try to formalize what it says. And so we're now at a point where when we finally finished a round of formalization of a given feature, we can take the CAT file, that's the sort of outcome of our work, and generate the English automatically from the CAT file to then put it back in the reference manual in this section here. So the English prose, specifically for the memory model, is produced from the formal model. And I forgot to say in the previous page, so we've got various landing pages for releases, but we've also got the development version that's over here on GitHub. And if you have questions or comments, please don't hesitate to write to us at this address here. Those are the tutorials I mentioned and various other pointers. So I'm going to recap the sort of initial level of support we had up until maybe 4 years ago or so, and the more recent work we've done. So originally, we could handle sort of user level examples, and I gave one here. So this is a message passing shape, hence the title MP, and it uses instructions that are release stores and acquire loads. So you can see two threads, P0 and P1, displayed in column. P0 here sets the value 1 to memory location X and sets the value 1 to memory location Y. And it does the second store with a release attribute here. It's the L of STLR. STR on its own just means a store. STLR means a store with a release semantics. And the release property means that the two instructions on P0 cannot be reordered, or more precisely that the first one over here cannot be delayed after the store release. On the reading side, we've got an LDAR, an acquire read of the flag, followed by a plain read, a plain load of the memory location X. So what we're asking here is, in the final clause over here, is whether we can get the flag with the LDAR over here, and sadly observe the stale value for X, which is 0, and neglect to observe the update of X. And so initially we could handle such questions. We then extended our reach to mixed size examples, and I give one here. And the question here is, what happens if the two threads P0 and P1 communicate via 16-bit memory location X in the following way? So P0 does an 8-bit store to X, that's the one highlighted in yellow, writing 1 into the least significant byte of X, and P1 does a 16-bit store to X, writing 2 in each 8-bit half of X. And so what we're asking is, if P0 does a 16-bit load of X, the one in purple over here, what can we see in the end, which is the question asked by the green exists clause. So this was more or less where we were in 2020, 2021, maybe. And so at a high level, the way we resolve those questions is as follows. So the ARM memory model gives us some ordering requirements of memory accesses, and intuitively it states which local orderings must be respected by hardware, also on each thread, on each core. And those constraints forbid certain shapes in program executions, and typically we're looking for cycles in an overarching relation that's called ordered before, which consists on the one hand of local orderings, so that's the locally ordered before relation in the spec, and interactions between threads, which we call observed by in the ARM spec. So concretely, this looks like this. So on this side, I've got an excerpt of the CAD file. And you can see that the relation that we called OB for ordered before is made of observed by, so the interactions between threads, and what we called hardware requirements, which are the local orderings per core, and the transitive closure of OB. And then we require that OB must be irreflexive, because it's transitive. Essentially, that means it cannot exhibit a cycle. On the other side, you will see the English text that actually appears in the reference manual. That's a direct transliteration of the CAT. So concretely, it looks like this on my user level example. So the way we examine whether a litmus test is valid or not is by generating the possible executions of the program. And so here, for example, the ping box that's labeled thread 0 corresponds to the semantics of the thread P0 here. So we've got, with label A here, a write event of the memory location X with value 1. And here the event B is the write event of the flag Y with the annotation val for release. And so I said before, the fact that this is a release constitutes a local ordering. More precisely, it participates in the relation that's called barrier ordered before in the ARM, and this is what this BOB arrow is for. On the other side is what happens on P1, the reading thread. So we read the flag Y with an acquire annotation, and we read X. And again, the fact that the first load here has an acquire annotation means that it creates a barrier ordered before relation towards the read of the memory location X. And then in between threads, we've got those colorful arrows, which are interactions between threads. So more precisely, the read of the flag Y reads from the right of the flag by P0, and the read of the memory location X is overwritten by the update of X made by P0. And those two specific interactions, again, participate in the ordered before relation, so that altogether, we've created here a cycle in the ordered before relation, from A to B via barrier ordered before, to C via read from, to D via barrier ordered before, and then back to A with another interaction called coherence after. So again, that's where we were in 2020, 2021, but this does not account for a concept that appears in the ARM that's called implicit effects. And so essentially we've spent the past 4 years, give or take, studying implicit effects. So I'll show you concretely what I mean by this. So here's the semantics of an LDR, load instruction, without any consideration for implicit effects. So what does an LDR do at this sort of level of abstraction? It reads the register X2 that's given here as an argument, and it gets from it a memory location X. It then reads X and gets from it some value, which happens to be 1 here as per the initial state in the litmus test. And then it writes back the value it's read, so the value 1, into the other register given as argument X1. And then for an STR, here's what happens. Again, at this sort of simpler level of understanding. We read, here we can read in parallel both input registers. So we read X2 and get a memory location X, and we read the value 1 from the other register X1. And with these two pieces of information at hand, we can write back the value 1 into the memory location X. And the colorful arrows between the effects of the instructions are what's called intrinsic dependencies. So they say, I need the information from the box at the top to feed into the box at the bottom. And here you can see that there's no need for such intrinsic dependency between the two reads of the registers for the store. So now, like I said, we've spent the last 4 years starting to formalize the notion of implicit effects. So essentially, or intuitively, you can think of those are the effects which guard the path towards accessing memory or faulting, for example. So they manifest in various places. For example, page table reads, or there's a feature that's called memory tagging, which guards the memory access with a tag check. So check that the memory location has the right tag, and if it doesn't, then you can't access the location, or instruction fetches. And so formalizing implicit effects also brings in to light the notion of intrinsic dependencies a lot more than in the simpler examples that I've given you. So at a high level, intrinsic dependencies convey the order in which a given instruction should perform its effects. And if we take into account accesses to page tables, for example, we would first need to read the page table entry of a virtual address X to get to a physical address. And in other words, the implicit read of the page table entry of X is intrinsically before the explicit memory read or write effect of the physical address. And there are several types of intrinsic dependencies. They don't quite contribute to the memory model in the same way. So all those implicit effects bring in quite a lot more subtlety, which I'll try to illustrate in a minute. So one concrete example of that is the VMSA, the Virtual Memory System Architecture. It's a subset of the ARM architecture. So, and essentially this pertains to accesses to page table entries. So here's a concrete example. So back to the load instruction here. So here, instead of pretending that I'm directly accessing the memory location X, instead I'm gonna talk in terms of virtual address X. So X here is a virtual address. And so before even being able to read the corresponding physical address, I need to have a look at the page table entry for that virtual address. And you can see here that a page table entry for us is a tuple. In particular, it indicates whether the page table entry is valid or not with a bit that's called the valid bit here. And in the example that I'm giving, valid is set to 1, so the page table entry is valid, which means, as per the semantics diagram here, we're reading the page table entry for X. It gives us an output address that corresponds to a physical address that we're going to be able to go and read. And here's the corresponding explicit read effect to the physical address. On the contrary, if valid is 0, so the page table entry is invalid, then we don't want to go and access any physical address, and instead we want to fault. And so the semantics changes here. We see that the valid bit is 0, and instead create a faulting event. It gets a little more complicated if we take into account what's called the hardware management of both the access flag and the dirty bit. So a page table entry doesn't only just feature the valid bit, it also features the access flag, which essentially tells you whether you have read permission. and the dirty bit, which tells you whether you have write permission. So in the simplest base case, if you don't have read permission and you try to do load, you're going to go ahead and fault. And if you don't have write permission and you try to do store, you're going to go ahead and fault. But there's a feature that's called the hardware management of those 2 bits that will, when, for example, the access flag is set to 0, instead of faulting, the hardware is going to set it to 1 and then allow you to go and perform your access. And similarly for the dirty bit, if, as in the example here, you've got the dirty bit set to 0, but you've got the management bit DBM here that's set to 1, you're telling the hardware to go ahead and set the dirty bit to 1, so that if you can then just go ahead and do your store without taking a fault. And so exactly how you set the dirty bit is not trivial. So essentially, you've got to read the page table entry, observe that the dirty bit is 0, but you've been mandated to make the update with DBM equals to 1. And then with a read modify write, which is the RMW arrow here, you're going to go ahead and update your page table entry to DB being 1, which then means you are allowed to go ahead and do your write of the corresponding physical address. See, just you can see that the semantics of just the grown massively, and that we've got to handle many different other effects that will contribute in some way to the orderings that we need to account for in the CAT model. So now that I've shown you very briefly what the sort of updated semantics look like, I can show you how we use that in a concrete example. So back to, just for a minute, to a user level example. So here we have 2 threads, P0 and P2. That's on purpose because in the next slide, I'm going to introduce a middle thread P1. That's going to be what the OS is doing. So on P0, P0 and P2 are communicating via a VAX that initially has the value 1. And thread P2 is updating X to the value 2, and thread P0 reads X twice with those 2 loads here. So the user level model says that it must not be the case that thread P0 first sees the updated value 2, the one that comes from P2, and then the stale value 1. So if you see the update from P2, you cannot go back and see the stale value. So, and this property must remain true regardless of what the OS is doing sort of behind the scenes. So system software should not work in a way that breaks the user level model. And so even if the OS is doing some work in the background and sort of fiddling with X, this example must still be full. So now could do it and be here and my origin. Here's something that you're doing meanwhile. So, and that's actually a copyright example from Linux that's been given to us by its developers. Artificial example. So what the OS thread P1 here could be doing in the background is disable all the accesses to the VA of X in the pink box here. And as you can see, it uses a number of barriers, DSBs here, 2 DSBs, and an instruction that's called TLBI that invalidates TLBs. And then we copy the value of the physical location of X via another VAZ to Y, that's the blue box here. And then we make X an alias of Y. And so P1's work in the middle should be transparent to P0 and P2, meaning the memory accesses of P0 and P2 should remain unaffected by all this remapping and copying done by P1. And so our model allows us to explain how this copy on write behavior works and why it's forbidden. So to reiterate, I think the point I'm trying to make is to be able to explain that sort of Linux behaviors, we've had to dive quite deep into the semantics of even basic instructions like loads and stores. So now I'm going to expand on how we compute those semantics. So, before I do that, I want to dive into what I called intrinsic dependencies, which are the arrows that mandate the order of the effects of an instruction. So again, at a high level, intrinsic dependencies convey the orders in which a given instruction should perform its effects, and there are several types of those intrinsic dependencies. And they're quite crucial, those dependencies, because they contribute to building the architecture dependencies. So, for example, address, data, control dependencies in the memory model. So I'll show you why that's the case on an example. So back to an MP shape. In fact, on P0, I've got the same piece of code that I had before. I do a store of X with value 1, and then I do a store of the flag Y with a release annotation. So this is to ensure that P0 won't be reordered. On P1, instead of using an acquire like I had before, I'm using an address dependency. So you can see here, I'm doing some computation on the registers, the register that the LDR uses here, the first one. And I'm using the result of the computation to set an offset of the second LDR. And this creates an address dependency at the user level that's represented by this address arrow here, and which in turn means that those two LDRs, those two loads, shouldn't be reordered. So now, how exactly do we determine that there's an address dependency? Is by using those intrinsic dependencies that I've talked about. So here you see the difference between this diagram and the next is that I'm going to expand the semantics of the both LDRs to all the effects, so the register effects as well. So for example, the first LDR of memory location Y. So I read the register X0. This gives me a location Y. Then I read the value Y, the value of Y, which is 1, and then I write back to the output register X1. So you can see there's an intrinsic dependency between the read of the location Y and the write, the register write. Then I do the XOR, and you can see that the XOR reads its value, so rather the value of X1 from the previous register write from the LDR, and that's represented by this read from register arrow here. And again, after reading 1, it writes back the value 0 after doing the XOR to the output register X2. This then feeds into the second LDR, again with a read from register, and we follow again with an intrinsic data dependency. And it's precisely this chain here of intrinsic dependencies and read from registers. This is how we define what an dependency is, or data or control dependency. It's we make use of those basic bricks here to then determine whether there's a dependency at the user level. So you can see how getting the semantics of instructions right, or as right as we can, has consequences on the user level, on the user model, sorry. So now, the thing is, at the moment, or rather maybe about a year ago, before Adrien started working on his PhD, the way we determine the instruction semantics is as follows. So we would look at a litmus test, make an educated guess as to what sort of implicit effects this instruction should or could yield, and the relationships between them. So all those colorful arrows, and then we would discuss if there were missing effects or missing arrows, or if certain arrows should land here or there, and that would sometimes have consequences on which tests would be allowed or forbidden, which behaviors would be allowed or forbidden architecturally. So it sort of works. It's a social process. We can make proposals and then discuss them with architects and our partners. But it can take a while. It's actually rather hard. We don't always get it right, and neither do our colleagues architects, and so it can take quite a long time to validate. But that's one way of extracting the truth, or at least the intent. Now, there's another source of truth or record of intent in the RMAM, which is for each instruction, there's a description of it in a language that's called ASL, the Architecture Specification Language. So here I give an excerpt of the code for LDR. I can point you to the actual full extent of the code if you want later. And what we're trying to do at the moment is, can we read this code and extract the semantics that we're interested in for each instruction instead of inventing them by hand and by discussing with architects. So this is not to say that we would not review with architects later, or that we can't sort of inform or work with educated guesses, but we're hoping that we can extract more systematically the semantics of instructions from the ASL code. And so, so I'm going to conclude here by saying that we're now developing not just a tool set for the memory model, but a tool set for ASL, for the Architecture Specification Language, which you can again find on the same GitHub, specifically in this directory here. And so we've got an interpreter and a type checker for ASL, which you're welcome to go and play with. And we're also writing the reference documents, definitions of that language. And we can use this interpreter in the concurrent context as well, meaning we take a litmus test with its handwritten semantics. It gives us a given result. And we can compare it with the litmus test where we use the ASL semantics and see if the results agree. And that allows us to discuss with our colleagues at ARM whether the ASL is faithful to the intent, or whether the semantics that we've drafted by hand and reviewed with them actually missed the case, or perhaps if actually both sides are not in accord, if actually we want both behaviors or something else altogether. And so that allows us to have another data point, so to speak, to determine the semantics of instruction. All right, that's it for what I wanted to show you, but I'd love to have questions or comments if you have them.
Jade. Questions for Jade?
Hello, and thank you for your talk. Are you doing it for a fraction of the ISA of ARM or the entire instructions? Because if I remember correctly, ARCH has like 1,300 instructions, considering all of the flags and flavors of one same instruction. So are you aiming at formalizing all of them or some of them? Because things could be really manually intensive.
Exactly. So that's one of the motivations for trying to extract the semantics automatically from the ASL code, right? Is if we keep on doing this by hand, of writing those graphs for each instruction by hand, we will never see the end of it. But if we can take the code that's in the ARM and generate it from there, then there's more hope.
John.
Could you clarify the various litmus tests and graphs that you've shown for these instructions? Are they the semantics of the instructions, or are they just properties of the instructions? And could you clarify exactly like what is the ground semantics of these instructions?
So this is an instance, right? But the semantics of the instruction in a herd is what's going to generate those graphs. So I guess what you're asking is whether that graph is just one example property of the instruction. Is that correct, John?
Yeah, I think so. Yeah, so yeah, okay.
So that's not the only.
You could have many.
Yes, exactly. That's one example of what can happen. But obviously, I can't fit them all on the screen. All I wanted to say is that you're going to have to contend with quite a few more new types of effects, and what are the relationships between them. And that's one example of what can happen.
Thanks.
Does that make sense?
Yes.
Okay.
The person next to Matt, and then Simon, and then we'll have to move.
Hey, thanks for your talk. So all this is architectural. So do you plan at some point to include speculative execution into these models? Because like transient execution attacks, they rely on orderings and all the page table stuff you mentioned.
So if we had infinite time, probably at the moment, it's not on my team's to-do list for the next year or so.
Simon.
But you might notice there are quite a couple of papers that aim to sort of extend CAT and that sort of description of systems to speculative execution. In particular, works by Hernan Pons de Leon. So if you're interested, you could have a look at that.
Yeah. Simon.
Oh yeah. So some implementers of ARM want to deliberately have subsets of the behaviors available in the memory model. Can those implementers use these tools to reason about the subset that they particularly want? So if they want to turn to a TSO mode, does this help them answer questions about strange or stronger dependencies that should be present to preserve TSO ordering?
So are you asking, I think one way of understanding what you're asking, but I'm not sure if that's what you're really asking, is you could swap the CAT file for a TSO one, something like that. Is that what you're asking? But keep the ARCH instructions.
Yes.
Yes, I don't see why you couldn't try. Yeah, I don't see why you couldn't try, but perhaps if you could give me a more concrete example of what you're after, I can help set it up.
I think I would have to think more, but maybe I can email you.
Yeah, absolutely. But at least in principle, if you want to just swap the CAT file to something else, stronger or weaker or just different, I don't see a priori something that prevents you from doing it. If you do find something that blocks you, I would love to know and I would love to help. So do write.
Okay, thank you.
Yeah, you're welcome.
Thank you so much, Jade. Let's thank her again.
Thank you.